Hello, everyone, and welcome to today's SANS webcast. Catch me if you can. My name is Keaton Nguyen, and I'll be moderating today's webcast. Today's featured speaker is Matt Bromley, Mandiant Senior Consultant. If at any time you have any questions for Matt, please enter them into the questions window located on the GoToWebinar interface. We'll be answering them during the Q&A session at the end of the presentation. And with that, I would like to hand it over to Matt Bromley.
Thanks, Kit. Appreciate it. Good morning, afternoon, evening to everyone, wherever you may be joining from. Appreciate you taking the time out to hang out with me and some cache artifacts today. So like Kit said, today's presentation is Cache Me If You Can, and we're going to take a chance to walk through some extremely interesting Windows artifacts and see if we can't hopefully increase our DFIR toolkits and arsenals just a little bit better. Just a quick agenda of what we're going to cover today. I'm going to talk a little bit about who I am. I like to say that's the most boring slide in the presentation, so I'll fly through that quickly. We're going to examine why this matters. What's the importance to me as a forensic investigator? Why do I care about these artifacts? We're going to briefly take a look at the Windows application experience and compatibility and understand why that provides the artifacts that it does and what it means for us as an investigator. We're going to talk about some forensic shim artifacts, and then last but not least, we'll wrap up, and I've got a nice little kind of analysis technique in there as well. That being said, we're going to take this webcast and go over kind of the overview of the shim cache and the application experience and the app compatibility and the overview of some of the artifacts. There are some extremely technical deep dives into the hex level of these artifacts, and I'd highly recommend if we don't get into them here, take a look at them offsite as well, but we're going to cover a good deal, so I'm looking forward to this. So jumping right into it, like I said, I'll quickly cover this part. I'm currently a senior consultant with Mandiant. We are a FireEye company. I've got over 4 years experience with primarily a focus on data breaches, incident response, digital forensics, and network security and monitoring. Although I will admit that my work experience has taken me through kind of all avenues of IT and what it may be. And some days I feel like a forensic investigator, and other days I'm the firewall guy sitting inside of the room. Just depends on what's needed. My work experience has ranged from small regional shops. I've worked 4 employee cases before, all the way to multinational Fortune 50s who have supported over 200,000 employees globally. I'm a huge advocate of working with and developing open source forensic tools. Actually, a lot of the tools that we talk about in this webcast are open source tools themselves, so I'm very, very happy those are out there and available for us to use. And more importantly, I love to share, learn, and help others improve because that gives me the opportunity to learn myself. So I hope at least one person learned something on this webcast. If so, I feel like I've done my job. After this and going forward, don't hesitate to hit me up on Twitter. I've got a GitHub page that I really do my best to commit to and maintain code on, and then I try to blog as well. I'm sure as every investigator knows, there's just times of the year where it seems like everyone goes dark because we're just so busy, but I do try to share when and what I can. That being said, this is a SANS webcast, and I wanted to make sure we also talked about, and I apologize for the drastic change in colors on this slide, but hopefully it caught your attention, which was my point. I want to make sure we do give a plug and a shout out to our upcoming Data Breach Investigation Summit here in Dallas, Texas. It's going to be from September 21st to the 26th, so about a month from now. Awesome security and forensic courses being offered, and then there's also going to be some bonus summit talks in there as well, where we've actually got some of the experts I talk about during this webcast, or some of the experts in our DFIR field who are actually coming and giving great discussions as well. There's a discount on the course if you register before 9/6. There's hotel deals, so if you are looking to increase your toolkit and your forensic analysis arsenal whatsoever, highly recommend you check out this summit. It's going to be a great event, and there's going to be a lot of good resources and a lot of good knowledge there at the event. That being said, let's jump into why does this matter? As a forensic investigator, why should I care, for lack of a better term, about these artifacts? Well, I wanted to put forward this statement, and if you've taken a SANS course, no doubt you've seen it. I think it's actually in the kind of header slogan for 4526 by Alyssa Torres and Jake Williams. But as a forensic investigator, really think about this statement, right? Malware can hide, but it must run. And not to echo the sentiment of all the SANS instructors who have said this before, but this is an extremely important statement when you are analyzing a system that is potentially been compromised or has definitely been compromised and you're trying to figure out what happened. There are a million places on a host that something can hide itself, and it seems like every week we've got a new blog post of someone who's figured out how to hide arbitrary code A inside of arbitrary place B that no one's looked at before, and then we see a whole flurry of parsers and artifacts come out. But remember that regardless of the hiding place, the malware's got to be able to run. It's got to be able to execute and do its job. And if you think of malware coming onto a system as kind of a funnel, when it hits the system, there's a million places it can store. But as the funnel narrows down, we get down to it has to execute. And the execution of a application or a program or a process or a service is a much smaller and well-defined process per Windows than it is of what folder do you want to place this in. So that being said, our malware authors are continually improving the methods by which they hide their malware. This is no secret to anyone who's been doing investigations for, I'd say, probably 6 months, but as the years tack on, you definitely know that it's getting better. Malware authors are finding new ways to hide code, new ways to execute code. Like I said a couple minutes ago, they're finding ways to hide it in places that no one was even looking at before because someone back somewhere decided that a key should be 500 bytes, but they're only going to use 2 bytes of it. Therefore, the other 498 are available for code to be stored in. Not only are they finding ways that they hide it, these persistence mechanisms are growing and becoming more intricate themselves. It's almost a study now to think about how malware can persist on a system. Not only that, but we're also, the reason why we need to consider the reasons of how malware runs is we now have environments that are extremely bigger than they used to be, and we're running multiple versions of multiple operating systems. And that's not necessarily anything new, but now we're seeing it at scales that we had never seen before. It's not an issue anymore, right? Hardware is a lot cheaper than it used to be. It's not an issue to see an environment where you've got Windows 2003 all the way through Windows 2012 working and commingling together, and you've got users who are still on XP, and you've got a dev shop who's all the way up to Windows 10. So as a forensic investigator, if we walk into an environment, not everything is going to be Windows 7 SP1 and Win2K8 R2. Boom, that's it. That gives us a fairly static board with which to jump off of. So as an artifact, if we know that our malware's got to run, then we need to understand the different parameters that it may run in as well. So as we see our environments begin, or not begin, but as our environments continue to remain diverse, we need to make sure our thought process is diverse as well, and we can approach these artifacts regardless of what system they're on. The second reason of why I think this matters, it's very, very, very simply illustrated. As the time since an incident continues to grow, the amount of forensic artifacts available continues to decline. Logs roll, right? Users are going to use. We're going to shut down, we're going to reboot, we're going to redeploy, we're going to destroy hosts, we're going to delete this, we're going to remove that, USB drives get lost. There's a million different things that happen from the start of an incident or the start of an alert all the way up to when we may actually get on site. And that poses an interesting difficulty for DFIR investigators because we are constantly living in the past. And that's not a bad thing. It's not something to be worried about. It just means that if we're going to be living in the past, right, we need to be more cognizant of what is in the past and what's available to show us what was actually happening back at a point in time. I kind of like, as an IR investigator, being able to live in the past. It keeps me fresh and keeps me thinking about what may have happened at that point in time, and we're always uncovering new artifacts because of that. But that being said, more importantly, understanding that time only can hurt us in some ways, and time only makes artifacts go away. We need to have as much information as possible, right? Not only do we need to know where the malware is, we need to know what happened on either side of that malware. We need to know what was happening before it, what was happening after it ran, what was happening on the system in my environment before and after. So the goal of understanding these different artifacts is to paint a picture of attacker activity, right? What happened? And the Windows cache artifacts that we're going to talk about, they're more of about what happened when in a point of time. Like I said, we're constantly peeking back, so we need artifacts that can hopefully stand the test of time as well. And luckily, in a majority of my experience, the cache artifacts, or some of the cache artifacts, have been able to do that. Before we jump into them, and before we before we kind of move into looking at the Windows application experience and compatibility, think about some previous investigations where you're looking for, or you were looking for, presence of malware, execution of malware, or really trying to understand what happened after that malware was run. There are some times where time is against you and you're going to have a lot of question marks surrounding all of that. What I'm hoping is that some of these artifacts can help kind of decipher that or help understand what that may have been. And going forward, we've got something additional to add to our toolkit. Before we jump into the Shimcache artifacts, or the application compatibility, let's first take a look at why this even exists. Why is this even on the system? Why did Microsoft put it there? And what were the engineers trying to achieve? So the long word to define this is Microsoft Windows Application Compatibility Infrastructure. We can also call it the Shim infrastructure. I'm going to also call it the Shim infrastructure. This was actually designed and put into place, XP onwards, to help mitigate software breaking due to upgrades and improvement. Now, I've got the quotes in there for various reasons. Not only are they meant to be kind of a pun on an improvement or an upgrade that breaks something, but it's also meant to kind of highlight the fact that you may have programs that, and if anyone here works in industry, works in enterprise, you certainly know what I mean. You have programs that are written for an environment or for a system at a certain point in time, and they're not rewritten for further points in time. It's a version, it's running, it's generating tens or hundreds of thousands of dollars a day for the business. There's no one who says it needs to be rewritten, and the code starts to get very outdated. Well, Microsoft continues to update their code. So it became a business issue of, you can't force me to upgrade and tell me that my old legacy applications aren't going to work anymore, right? There's a point in time where developers have to be able to say, a company cannot afford to take software down. It just doesn't happen. So what Microsoft did instead is said, all right, fine, we will build in the opportunity for older legacy applications to reference former versions of code, if you will, and run that way. So it's actually, if you think about that description, shimming is actually just API hooking. So when you've got, at a very, very high level, when you've got an application running that needs to reference older code, it actually reaches out to Windows and says, hey, I'm looking for XYZ, and Windows says, oh, okay, that's older than what I've got, so here's the shim code instead. And the shim code is inserted, and the application is able to run with the code that it expects. Windows understands that it's running with older code, but it really doesn't make any difference to the user whatsoever. So there's a lot going on in the background that Windows is doing to help make sure applications are running correctly and running efficiently. And I know that's not an avoidance of BSOD, and it certainly does not prevent breakages from happening. But if you took older code and tried to run it on a newer operating system and Shimcache was not there, you would not get as far as you may get with Shimcache there. And the beautiful thing about it is it allows the developers and it allows the company to continue to upgrade the underlying operating system, but maybe hang on to that legacy code. But for forensic investigators, it gives us a fantastic artifact. And let's think about some of these points really quick. It's an API hook. It redirects API calls from Windows to alternative code, which is the shim code. So we've got a file, or we've got an application or a process accessing multiple different Windows artifacts that are then being used to redirect. Every time we see a hook, every time we see a DLL being accessed, every time we see code being pulled in, there's going to be an artifact there. So to my earlier point about time versus artifacts, the closer we are to an incident, the more artifacts we're going to have about what the application was actually doing. Now, to a DFIR investigator, it may not be super important to understand, oh, this is old code, and therefore it's loaded shim code instead to help prop up its older development. But what it gives us instead is an understanding of, if I see this, there's a very good chance I'm going to have shim artifacts as well. And then this is a really good kind of graphical representation. This is actually sourced from TechNet, full credit down below. And it just kind of gives you a picture of how an application with or without shims is going to run. The application looks at the import table, goes to Windows, Windows says, boom, here you go, and we run. With shims, the shim code is just inserted in between the import table and Windows. So from an artifact point of view, and from a kind of process and overview of why shimming is there, it's very important from a business purpose, but the beauty of it is it gives us those artifacts as well to look at. So as we go through and discuss the certain artifacts, I hope this kind of outlines and makes sense as to why shim code is there and why the artifact helps us. When we see shimming done in place, we expect that when a process creation begins, Windows is going to look for the app compat flags. If application compatibility is needed, there's going to be flags there. If they're present, then there's actually a database that is referenced through the shim engine and looks for the various code that's needed. As the flag comes forward, as the code comes forward, there's a parsing through the shim database, and if required, meaning if the older code is needed, then the shim engine DLL is loaded, and we've now got code that can run. So again, multiple artifacts on the system, and this can help us in a couple different ways. If we're watching something like Process Monitor, we're watching artifact creation, and we are seeing DLLs being loaded, or we're seeing code being loaded that may be something we weren't expecting, there's a possibility that we are seeing shimming as well. But more importantly, we've got the other artifacts we can look at. So that being said, let's jump right into some of our forensic shim artifacts and see what's available. We're going to start with the recent file cache. This may or may not be known by many investigators, only because it is extremely volatile and difficult. And we'll take a look at that, and then we'll jump into shim and mcache hides as well. So the recent file cache is located inside of the C:/Windows app compat folder. That's right, Windows since XP has had an app compat folder. So all of these artifacts have been sitting there for years and years. And inside the program subfolder, there is a recent file cache.bcf. This is typically going to be found on versions older than Windows 8 or 10 because of the change to mcache, which we'll talk about shortly. And it is a temporary storage of recently executed applications. And by temporary, I mean extremely temporary. I'm sure the bold letters, highly volatile, have jumped out at you. Well, it's important to understand what may cause something. If I have a file inside of my BCF, what does that mean? So it's going to be new programs, and new may not necessarily mean new to the system, new to the user, or new to the environment. They may have been copied somewhere, or they may have been downloaded. And when we also will see first runs of known programs in there as well. You'd find it interesting to think that something like notepad.exe or calc.exe may show up in the shim cache, because you'd think, why are they written on code that needs to be shimmed? It's not necessarily saying that they're shimmed, it just shows up as an executed program, which is one of the beauties of this artifact. Now note, the rfc.bcf is extremely volatile. It is cleared. There's actually a application experience program data updater. If anyone has kind of run Process Monitor, or you may have actually seen this in event log outputting as well, you'll see event log entries that say something like the application experience has started. The application experience service has stopped. That's actually what this is doing. The application experience is going through these various entries and then either committing them or not including them at all. Looking in hex, it's actually just a very simple hex representation of it's a hex representation of the list. There's not much of a structure to this, so it's actually really easy to parse, which makes it super simple to super simple to analyze. I've actually highlighted, so BCF being as volatile as it is, I quickly ran Windows Media Player and then took a screenshot of what we were looking at here. So you can see all it does is stores the file path. There is a little bit of a hex separation between the various applications, so you can actually parse it and put it into a structure. But for the most part, it's just a list of what was recently executed. If you can get to a system close to something being executed and run, then you may see these artifacts inside of the recent file cache. But again, you've got to get close to it. There are some great parsing tools out there for the recent file cache as well. Harlan Carvey's written a Perl carver. Patrick Olson has written a Python carver, so it just depends on what tool set your arsenal contains. And I just took a good example. I parsed the exact same file from that we just looked at in hex using Patrick Olson's Python carver. And you can see it just takes the hex versions or the Unicode store and just outputs them into plain text. So if you do happen to catch a recent file cache.bcf with artifacts inside, you can parse them. But remember, it's going to be highly volatile. But the beautiful thing about the volatility of this artifact is you're close. You're really close to the execution. So if you have something in there that is malicious, definitely a good point in time, right? And it gives you a frame of reference when you're doing timeline analysis or when you're doing overall system or IR or even environment analysis, it gives you a very, very good time frame of when that malware may have been executed or when that malicious program may have been executed. There's also, for folks using Ncase, Lance Mueller has also written a Ncase v7 nscript that will actually extract the RFC from memory images, allocate unallocated space, and the file itself, and will carve that for you. I'm not going to dump nscript code in here. There is a link to go grab this from Lance if you'd like. Didn't have an opportunity to spin this up and run it for a screenshot, but I have used it before in practice, and it does work well. And if you take a note, recovering the data from memory images and unallocated space, extremely important advantage right there. And if anyone has ever kind of conducted keyword searches across their images for known malicious programs, and you may have a random entry show up somewhere in unallocated, or you may have a random string show up somewhere in memory images, it's possible that you're seeing a recent file cache artifact being left there. As we looked in the hex dump, there's not much data or structure around it. So while it may look seemingly arbitrary, you may have stumbled across one of these before and not known it. It's extremely important to note that what you may have seen before that didn't really have any context may have actually been evidence of execution. So a great artifact to keep in mind, but the volatility makes it tough to really catch it at that point. Let's move on and talk about artifact number 2, which is the shim cache. Now, shim cache itself is not an artifact, but shim cache more of discusses an advancement that we see with regards to app compatibility. So the shim cache, again, is going to be primarily sub Windows 8 and 10. Primarily, there are some exceptions to the rules, and it's going to be stored in the registry as a string, as a registry value. For Windows XP-ish systems, aka Windows XP, you're going to find it in the app compatibility / app compat cache under session manager and control set. For non-Windows XP-ish, it's actually going to be in app compat cache / app compat cache key. And we're going to take a look at these keys, so don't open regedit and start digging. We're actually going to take a look and see what's in there. When I say non-Windows XP-ish, it's pretty much anything but Windows XP 32-bit is stored in a different location. And we'll break into those as well. So this is actually going to be much more extensive than recent file cache, not only in its history, but also in the details that it stores. It's going to have program execution and shim details. It's also got lower volatility. It can store up to 1,024 entries depending on the operating system. And we'll talk about, based on operating system, how those updates kind of break out or how those storage capacities kind of break out. So starting with Windows XP. Windows XP, the entries here are actually created when a new file is executed or when an application is modified and executed, kind of like we saw with the recent file cache. The registry entries are going to be 552 bytes in size, and it's going to contain a maximum of 96 entries. So if you are still looking at a Windows XP system, not only am I sorry for you, but you will have a max 96 in there. So again, we were talking earlier about volatility and how time may not be your friend, and artifact expiration. The shim cache can roll over. So if you are looking further back in time than you'd like to be, and you've had a very, very, very busy user or a very, very busy system, it is possible that you're going to lose some entry. Not possible, but there may be some entries that are related to your malware that are no longer going to be inside the shim cache. Oddly enough, each entry for Windows XP has a 400-byte header that starts with dead beef. That is the hex code. If you're looking at the screenshot, remember your endian in this. But yes, dead beef is the header for this. It's an extremely interesting concept to have dead beef in the header. But wait, it only gets better as we go on and we get into the intricacies of Microsoft developers. The header is also going to contain the number of entries in the record as well as the indices used by the cache manager. Remember, as the cache code is being hit, there's going to be indices pointing to what is being used and what's being referenced to by the executables needing to use the code. We'll talk about parsing tools in a little bit, but having a header that has a set length and also has a number of entries in there makes it really, really easy for our tools to parse through and break down the contents of what we're seeing inside. So kind of taking a look at the structure, and I've got to reference some former Mandiant colleagues of mine who have put out a great white paper on this. I've borrowed a couple of their structures. The entries for Windows XP is going to contain the full path of the executable, the standard information last modified time, the file size, and the last file update time. Notice none of these are file execution time or file creation time. Important consideration for when we're looking at shim cache entries. We do not have a time of execution. But again, we're not looking for malware must hide, but it also must run and be created. We're looking for malware must hide, but it must run artifacts. Shim cache can help us determine whether or not it actually ran. And if it ran, obviously it was on the system at a point in time. But remember that we may not have these. Shim cache entries on Windows XP are saved by WinLogon at the system shutdown. So think about that. You may be looking at a shim cache from a live system and have entries not yet written in there. I see a memory parser, which actually is already provided with volatility. There is a memory parser for AppCompat entries. That being said, they can also be recovered from unallocated registry or disk space. Yes, you can carve for them. Remember that dead beef header we were talking about? I'd be interested to run a search through some unallocated space for dead beef and see if we get a 400-byte string with a number inside and then some entries afterwards. I have actually worked a couple investigations myself where carving for shim cache entries through the unallocated space was the smoking gun and ended up going from a lot of question marks to all the answers. So if you do find yourself needing to look for shim cache entries and the immediate key does not have what you're looking for, I definitely recommend kicking off a carver if it's going to be that crucial to the case. You may actually find what it is you're looking for. Windows Server 2003, we see a big change. This is actually when it changes to the registry path appcompat cache/appcompat cache. Registry entries are now 24 to 32 bytes in length, and we can now go up to 512 entries being stored. So we've got a little more room in the registry. And we lose the dead beef header, unfortunately. Now we change to bad coffee, and I say coffee because it's actually C0FFE. And the header also contains the number of entries. So not sure how Microsoft went from dead beef to bad coffee, but in any event, I'm sure there's probably some great stories behind that, but this is way too much of a linguistic coincidence to be just that. Entries are going to be updated for new executables or existing executables with path changes and modifications. I think we're starting to detect a trend here, right? As something is introduced to the system or as details are moved around on a system, we're going to see updates being pushed through, and basically we're going to see Windows saying, hey, I don't know if I've seen you before. Do you need shims? Anything I can do to help? Now there are differences between 32 and 64-bit. Take a look at the table to the right side of the screen, and you'll see that we've got some different details being stored in there. 64-bit actually stores an additional entry. Moving on to Vista and Server 2008. We, again, are still 24, 32 bytes in length, but now we can contain up to 1024 entries. We've got a couple pieces of information added, which are the insert flags and the DW flags. And the file size has now been taken out. So from a Microsoft point of view, from a Windows point of view, we see the registry expanding, or we see this particular key expanding and saying, okay, I'm going to store more shim details about more executables so that way I can help things run faster, or I don't need to reference the database every single time. I'm not sure what kind of performance enhancements that we are getting by increasing the size of this key, but as a forensic investigator, if I see something jump from 96 max entries to 1024 max entries, I love it. I absolutely love seeing more data in there, more execution history. But if anyone has parsed a busy shim cache, you're going to start to see now why your files appear to cut off at a certain point in time, or why you may not have had entries that you expected to be in there. And oddly enough, now we're also starting to see applications being added without execution, which is very interesting. That's right. Applications without execution are being added to something that tracks application execution. Well, what we're seeing is we're actually seeing Windows Explorer, as it has been upgraded and parses through more data and provides more data to you. We're seeing exe metadata being parsed, and if a potential shim may be needed, we might see those details added to the shim cache. So that way, when the system runs, it says, hey, do I need to insert any shims for Notepad 1. Oh, yes, I do. There it is. Okay, here's your shims. So it helps the system run a little bit faster, but as forensic investigators, like I've always said, it gives us more to look at. It gives us more to think about and gives us a better artifact base. So we'll take it. Thank you, Windows Explorer. We love it. Moving on to Windows 7 and 2008 R2. This is actually where we start to see another change in the header. And we start to see changes in our registry as well. So our registry entries are now 32 or 48 bytes in length. We're still up to 1024. If anyone's ever wondered why a Hive is so big, it's starting to make sense now that you've got all these ridiculous space allocations. Each entry now has a 128 byte header, and now we've gone from bad C0FFE to bad C0FEE. I guarantee you there's a whiteboard somewhere in Redmond that explains why it went from FFE to FEE, and do you know how to spell coffee, and there was probably some shaming going on. Of course, neither are the correct spelling of coffee, but in any event, we've only got limited room for a header, right, Microsoft? And it also contains a number of cache entries. The reason I like to highlight that our headers contain our cache entries is because it gives our forensic tool creators and also our analysis mechanisms a better way to checksum against what we should see. If we should see 1024 entries and we've only got 1,000, there's something wrong with our parsing. What other data is being stored in there? Or what are we not parsing correctly? Again, we've got potentially non-executed applications being thrown in here. However, we'll talk about this in the next slide. There actually is a way to detect execution now, which is important. And our timestamps are still recorded as standard information last modified times. So taking a look at this structure, one of the first things I want to point out is when we started with Windows XP, we had 2 file times being recorded. Now we're just down to 1. The most important thing to remember as well about our shim cache is that we're looking at the last modified time. So don't parse shim cache and say, oh, this is when everything was executed, because that is an incorrect statement. This is when everything was last modified. It pulls from the SI, so that gives us an MFT artifact that we can go take a look at. And there may be some cases, if anyone has looked at an MFT entry, where your SI creation, access, and modified may match up or may be very close to each other. That may be the first time the file is put on the system and then executed immediately. So whilst I can't say that shim cache is evidence of file creation time, if you've got malware that kind of fits within a bucket of hitting a system, being run immediately, and then removed from the system, you're going to start to center very closely around execution time, or sorry, around creation time. And we'll take a look at this in an example a little bit later on. Like I said earlier, we do now also have evidence of whether an application was executed or not. We've got insert flags being put into our data now. And if they're written with a value of 2, we've got an indication of execution. The DW shim flags are going to relate to the compatibility database. And there's still some research being done. There's still some thoughts out there, but there's now a QW blob. The QW blob size is going to dictate the size of the offset, but the offset, the blob offset, seems to relate to whether or not the executable was an installer. And the reason why this may be spawned is because an installer is typically going to spawn other executables. So there's going to be some more data kind of wrapped around an installer, which spawns others, versus an executable running just once or running by itself. If you'll notice too, as these entries kind of grow and get better, you can see from a software development point of view the details that Microsoft is trying to include to improve the user experience. Remember, this is the application compatibility experience. So we're trying to make sure that what we can run stores, and these details are actually being stored to help support Windows and help support application execution. Hence the shim flags. We're now relating to the compatibility database. So if anyone needed to kind of go and take a look through this data and understand what did my malware need to shim, what kind of code was it possibly written with that needed to be shimmed on a Windows 7 system, you might have a pointer inside of the database here that can point to that reference for you. Let's take a look at parsing these, this valuable artifact that we've got. And I say valuable because a lot of environments are primarily Windows 7 and Server 2008 R2. There are multiple tools available. I have to give a shout out to our Mandiant folks. We've got our own tool. You can find it at GitHub. It's a Python script. It's freely available. It can parse from the Hive. It can parse extracted keys. You can point it at your live system, and we can also look at mere XML files as well. Now, the thing to note about shim cache output from probably almost every tool I've taken a look at, your output is going to be returned with the most recent execution first. So you're going in reverse order based on execution per the output spreadsheet that you may get. And we'll take a look at this right here. Here's a good example of Mandiant's Python shim cache parser. Sorry, you can just point it at a Hive file. It's going to tell you what it's looking through, and it's going to output to a CSV file if you want. The -O switch is actually going to give you a CSV output. Starting at the very top, the tstheme.exe that we're seeing inside of System32 was the most recently run program that was committed to this registry key. Remember, we may have some sitting in memory that haven't been committed just yet, but this is what we're able to look at and say, okay, tstheme was the most recently executed application. Let's go back in time. Remember, the timestamp is going to be last modified, so it's not going to give you an execution time, right? It's funny to think that artifacts are stored in order of execution, but there's no execution time. But also that the last updated time is not there. Our file size is no longer stored. Those are mostly going to come back as NAs. But take a look at the far right of that screenshot, and now we've got an executable flag. That's that to flag I was talking about earlier. Was it executed or was it not? Now, a false in that category may mean it was metadata being read, may mean it couldn't have been run, may mean it was not run, but trues are usually what we're going to see, and falses may require a little bit of investigation, especially if you've only got falses for malware and no trues for that same malware. Eric Zimmerman has also written an awesome AppCompat cache parser tool. It's available over at his blog, binaryforay.blogspot.com. Eric's tool, I think, is great because it's Windows-based and doesn't require you to deal with a Python setup if that's not in your normal arsenal. Eric's tool is very simple. It's a /s switch for the output and then a /h. You can point it at the Hive. So I did the exact same test here for the system Hive, which, as we discussed, is where it's stored. And you see Eric outputs information from there in the same order. We've got our cache entry position, so our most recent first. We've got our path, and then we've got our last modified time as well. Remember, that's our only timestamp being stored in there, so we have to make sure we approach that artifact carefully throughout our analysis. That kind of wraps up the shim cache. We went through an overview. We discussed a couple parsers. Now let's talk about probably the new kid on the block, and I think one of the more exciting cache artifacts, which is the AMCache. So AMCaches are most recently on Windows 8 and 10, as well as Server 2012. And it actually replaces the recent file cache.bcf and the shim cache with an AMCache Hive. So now we've actually got a regf Hive being stored for these details and storing this information. It is also still located in c:/windows/appcompat/programs. So we've still got that appcompat folder. By the way, if anyone does go through and take a look at that appcompat folder, you'll see the shim database in there as well. There are some great technical overviews of that. We're not going to go into this deep dive here, but if anyone wanted to explore a little bit further, that is there. And like I said, it's now a Windows NT Registry Reg Hive. So now we've got a well-known structure storing all of this super useful information. So it allows, from a forensic tool point of view, it allows our tools to be a lot more successful. You can actually load an AMCache in something like Ncase and browse it natively as though it was a piece of the file system by viewing the file details. So if you are using some of those proprietary forensic tools, you can browse these as you would any normal Hive, and you're going to get some great information from them. The AMCache ups the game significantly. Look at that in big, bold letters. We now store a SHA-1 hash of our executable. I could not have asked for more. Well, maybe an MD5 Microsoft if you're listening, but in any event, we now have a hash related to our executable. So now we've got something else we can pivot off of. Whereas before we had a yes or a no. Look at all these different details we've got. We've got PE header information. We've got multiple timestamps, modified, created, full path, version, size, product name, program ID. I hope my excitement for AMCache is evident in my change in tone, how beautiful this is for our forensic investigators now. I really want every environment to now go change to Windows 8 or 10 just so I can have more AMCache Hives to look at. I don't need to highlight the last bullet point. You can already see the increased value that we're going to get from these artifacts. I'm just happy about having a hash finally for what's on there. These may contain data that's no longer available to us on the system. So whereas the AMCache went from a kind of point-in-time reference, the AMCache now may be a significant store of historical information. So if you're not looking at it already and you are looking at Windows 8, 10 systems in your investigation, I highly recommend you include the AMCache in what you're looking at. But understanding the structure behind these. So the records are grouped by volume GUIDs. That's right. If you plug in a USB drive or something external or a network share and you run an executable from those, it's going to be stored by GUID. So think about that for a second as a forensic investigator. If I pull an AMCache from a machine with only a C drive and I've got multiple GUIDs being stored there, I can go and match those up with mounted devices. Not only can I go match them up with mounted devices to understand what device this was run from, but I've also got really great proof of an external device. So if anyone here has ever worked one of those cases where someone says, no, I don't plug external drives into my machine, just give me your AMCache and we'll take a look and see what we've got there. Granted, there needs to be an executable on there that was run or was parsed by Windows Explorer, but still, I like having multiple arrows that point to the same place. So the structure is going to be a little bit different. We're not going to cover the full AMCAS structure because honestly there's A, a lot more research to be done, and B, a lot of information in there. But what we care about for the purposes of this discussion are the root file volume GUID folders. And inside of the volume GUID folders, we're going to have various entries, each one representing a program within the AMCAS. Now, I believe there's a long list of attributes that are going to be stored. You've got hexadecimal values, so A through F, and then 0 through 16, and then there's a 17th value and 100 and 101. So you have a possibility of almost about 20 keys to be stored in there. You're not going to have every single key for every executable. Some of them, like the screenshot we've got below here, we've only got 4 stored in there. We've got 100, 101, 15, and 17. Now there are mappings that talk about what each one points to, but more importantly, remember 101 is the SHA-1 of the file that we've got. And you can see here that this is actually an entry for me running Dropbox, or a Dropbox executable being run, the SHA-1 of it, and it looks like a timestamp in there as well. Sorry, jumped ahead too quickly there. So as you take a look through your AMCAS entries, have a look and see the various keys that are in there. I don't have a full kind of table breakout here, but there are some available online, and I can be honest and say that research is continually ongoing with the AMCAS Hive. So as more artifacts come available, as we understand more about these entries, as quite frankly more people start to use Windows 8 and 10, you will see the knowledge base on this increase. But at the start, we can already parse this artifact and get useful information out of it. Speaking of parsing, I'm going to give Eric Zimmerman another shout out because he's written, I think, a fantastic AMCAS parser. And the main reason why I like to promote Eric's, amongst others, is primarily for the second bullet point there. Eric took a look at the SHA-1 values and the various attributes of legitimate executables, Windows system executables that we would expect to show up in AMCAS, but are going to be there. From a forensic point of view, if we can store 1,024 entries, and 1,020 of those entries are legit whitelisted Microsoft applications, I don't want to have to dig through those on a daily basis. So Eric's tool actually gives you the ability to say, if you know what you know, give me a whitelist and I will remove those entries for you because we're establishing a level of trust. Let's look at the other side. I have a list of SHA-1s that I know are bad. Eric's tool is also going to let me blacklist them as well. So we can give a whitelist or a blacklist, and we can say, show me bad, or take away everything that's good and only show me the unknowns. I'm not going to go through too many other features. I think Eric actually just released this tool, or an updated version of this tool, where he's got other metrics built in and other cool new features. But if you are looking to look at AMCASes, definitely go take a look at Eric's tool. It's going to give you a lot of information on the output and really help you as an investigator dig faster and get down to what's bad and what shouldn't be there. There's also a Python script Willie Ballantine, a colleague of mine, has created, and he's written and has made available. Yogesh Khatri has also written NCase v6 and v7 parsers as well. That's available over at his site, swiftforensics.com. And these actually output to the forensic console. So if you are an NCase user and you're looking to parse the AMCAS and you don't want to sit there and click and scroll through every single hive, take a look at his parsers, and you can just throw those at the AMCAS and it'll give you the information right back out into the console. So as you can see, despite this being a relatively quote-unquote new artifact, I know Windows 8 isn't new, if you will, but you know, it's definitely not as prolific as others. We've already got people approaching the analysis and approaching the parsing of this awesome artifact. So if you are looking at it, there are tools out there to help you. So that being said, we've kind of looked at a bunch of different a bunch of different cache parsers. I wanted to take a couple minutes and just talk about an analysis technique. I know we've discussed it and we've kind of circled around the idea, but let's take a look at how we would actually use these to analyze. Now, in this case study here, and I'm using case study loosely, I'm making a lot of assumptions about a forensic investigative team. So if any of these bullet points don't line up with your normal process, or if I've made assumptions about imaging a host or collecting information or about actually identifying something, please excuse the assumptions. But for the case in point, it's important to know what we're looking at. So let's say your SOC gets an alert of malicious traffic originating from a user workstation. I'm not going to quantify what that alert is. Let's just say, hey, John Smith is doing something bad because his system's blowing up. We go and collect targeted artifacts from his host, including the registry hives and the event logs. Registry hives and event logs are important because our registry hive is going to contain our app compat. Oh, sorry, I should have mentioned John Smith is operating Windows 7. So keep that in mind, and our event logs. we parse through the event logs, and we've got multiple AV errors hitting on the file c:/windows/ocmpgpk.exe. Something is not right. AV does not like this file whatsoever. Our event logs show an admin user logs in, AV is disabled, and all of a sudden the errors stop. We don't know if the errors stop because of the disabled or because, the errors stopping does not mean that the program actually ran. It just means that AV is no longer picking up on it. So if all we had done is parsed event logs, all we would see is AV doesn't like this. User came in and disabled AV, and then boom, AV alert stop. We may have no other context around what happened with this executable at that point in time. But the beauty of this is we have timeframes that we can pivot off of. Not only do we have timeframes, we also have a file name as a pivot point as well. So the analyst says, I just watched this webcast and I learned a little bit about application execution. Let's take a look at the shim cache and see what's there. So this is actually the same screenshot from before, and if anyone kind of picked these details out before, then bravo. But if not, let's kind of walk through and take a look. So we've got our starting point. Number one, we've got our bad executable, oscmpgpk.exe. Again, from our event logs, we've got a time frame of when this was attempted to be executed, and now we've got a true flag that it was executed. So we now have pretty good idea that once the AV log started, the admin user probably tried to execute it again. But let's take a look and see what else we've got around. Remember, the shim cache can not only prove execution for us, it can also kind of give us an idea of what was happening around that. If you walk 10 steps and I catch you in step 5, I can make an assumption that you were walking 4 steps previously and you've got 4 steps left to go, or 5 steps left to go. What was happening around execution? Malware doesn't just run by itself on a system because no one put it there and because it just appeared and said, I think I'm going to run on this user's laptop tomorrow. Nope. Take a look. We've got PSExec entry, or sorry, PSExec entries lined up on either side of this malware. Now, for anyone who hasn't seen this artifact before, PSExec is actually evidence that is put when someone tries to run PSExec against a host. So now we've got a remote host attempting to connect with this machine. We've got malware wrapped in the middle of it, which is definitely going to raise some flags. But immediately, I know that based on where this malware sits and based on execution artifacts around it, I need to start, there's going to be at least another host involved. There's going to be other artifacts we can take a look at. And here's another quick little tidbit too. Take a look at the execution, or sorry, at the last modified times of PSExec. Notice they increment by seconds as each executable, or sorry, as each executable is recorded. If this was the same executable, we would expect the timestamp to be the same. But what we're seeing instead is we're actually seeing the creation of PSExec on the host. So you may have some artifacts. Now that's not always going to be indicative of that, but you may have some artifacts that are created and run as a result of another action, right? Evidence left by another process. It's going to take the timestamps of when it was put there. So we can see the increment in that. And notice we had 4 seconds where the malware wouldn't run. Then all of a sudden we have an execution flag, and now we've got PSExec running. But what else does the shim cache tell us? I've got 2 other executables here that I'm also interested in. This top lzagu.exe and this dllhost.exe. So let's put this in context and kind of back up. We started with a SOC alert from an AV hit on one application, one piece of malware that wasn't liked. We pulled 2 types of artifacts from the host. So we didn't go out and kick off a full image. We didn't go out and do all this kind of stuff. We pulled back registry and event logs. Now, granted, there is a better laundry list of quick triage artifacts you should pull back, but let's look at just those 2 because that's all we need. We've got AV alerts. Something doesn't like this executable. Let me parse shim cache from the registry. Just based on this parse alone, I can see I've got another system involved. I've got potentially a compromised user account that I need to look at. I've got some reconnaissance being run. I've got ipconfig being run after the malware runs, and I've got 2 other executables that I need to go take a look at as well and see what else these executables are doing. These aren't normal names. These aren't normal locations for normal names. So we went from one AV alert to quite a lot of information and context just based off of 2 artifacts. Shim cache helped us a lot with that analysis. I hope this kind of little technique, it was 2 slides and 1 screenshot, but hopefully it kind of illustrated the value of what we're seeing and how this artifact can help you in your investigations. So that being said, let me kind of wrap it up and talk about give an overview of some of the things we looked at. as I've said multiple times, as forensic investigators, we are constantly looking for new artifacts to paint a picture. If you have not been looking at cache artifacts before, I would definitely recommend including them, primarily because of the value we just got out of the simple screenshot that we took a look at. Knowing the volatility of these artifacts and understanding the differences between systems is going to also help you understand how to analyze them, how to parse them, or how to parse them, how to analyze them, and then how to portray the story of what it is you're seeing to your executives, to your team leaders, or what it may be. And more importantly, there are multiple parsers available for each type of artifact. So by no means are you restricted to learn something that you didn't know, or you are restricted to running a Python environment so that you can run these scripts. If you've already got a forensic arsenal, there's most likely a tool that you can add to it, and it's going to complement it, and it's going to be a big part of it. So if you want to start taking a look at these artifacts, if you want to include them in your normal processes, go out there and find the tool that works for you. Just make sure you're understanding the output and interpreting the data that's parsed correctly. I would be a fool if, as part of this presentation, I didn't talk about the shoulders of giants upon which I'm able to stand. SANS is an awesome organization. If anyone here has taken Forensic 508 or 526, I'm sure as well, the APCA compatibility cache is not going to be a secret to you. These are covered in those courses, but SANS has done some great things as well to advance these. Mandy and Eric Zimmerman put out some awesome tools. And then blogs below, Corey, Harlan, Yogesh, you guys have put out awesome research on these. And as a forensic community, we continue to do great research on these artifacts and to help each other out. So I'd like to say thank you and obviously open it up to Q&A. But I want to make sure we give one more shout out to the SANS Data Breach Investigation Summit coming up in about a month here in Dallas. Again, if you are looking to increase your arsenal, please make sure you check out this. It's going to be a great melding of minds in a great city. It won't be too hot, I promise, down here. But in any event, discounts on hotels, discounts on courses. Hope to see you there. With that, take any questions, but thank you everyone for attending. I hope you were able to at least learn something. And like I said earlier, I'm available on Twitter, email, blog, Git, whatever it may be. Feel free to reach out. I'd love to meet as many people as I can from the community.
Folks, at this time, if you have any questions, please enter them into the questions window. Look it out in the GoToWebinar interface. We'll be answering them momentarily. Matt, our first question is, if you have an improper shutdown, will it still write to the cache?
So in cases that I've seen, not necessarily. So it's going to require a graceful shutdown for some of the executables to do what it is that they need to do and to write to the cache. You may catch cache writing kind of in the mist. It depends on where the application is. It depends if the application experiences clearing out the recent file and pushing it through. But that being said, there are cases where you may not have caches written to the registry or to the Hive based on the way that the system was shut down, which is why we definitely encourage, if you can, and if you're not seeing what you expect to be seeing, take a look at memory. And obviously an ungraceful shutdown may mean a lack of memory, but if there's a Hyper file or something else you can look at that is at least up to date, you may have artifacts in there you could look at.
The next question is, in the last Simcache example, how do you know if another host/machine is involved?
So I went off of the assumption that PSExec, which is a remoting tool, is trying to connect to a machine. And the the creation of PSEXE SVC is actually created when someone uses PSEXEC remotely. It is the tool that supports the remote operation of PSExec. So the reason why I kind of made that assumption is because I'm seeing artifacts of a remote capable tool.
Folks, again, if you have any questions, please submit them to the GoToWebinar Questions tab. The next question is regarding carving Simcache entries and parsing them. Do you have any file headers of preference?
I do not. I would say the dead beef or the bad coffee variations of spelling would probably be the best indicators that you may have something to be carved. But I would say beyond that, they're most likely going to follow. And we put the structures in the slides, and the slides will be available. But hopefully, if you've got a full entry, and obviously that's the caveat with carving anything, if you've got a full entry in there, it should follow that structure. So I'd say look for those headers and go from there.
The next question is, how is the executed flag derived from a Simcache entry?
So that's great question. So it's the number 2 flag, like we mentioned before. And I believe, at least based on the experience that I've seen, that this is not 100% conclusive, but that's going to be kind of the line where we talked about, was the executable directly ran, like someone is forcing it or asking it to run, or was the Windows metadata parsing that executable, or sorry, was Windows Explorer parsing the metadata of that executable, looking for the app compat flags, and threw it in there based on the presence of those flags. So the true false may sometimes be indicative of actually being run or not.
And with that, if there aren't any more questions, I would like to thank you, Matt, so much for your great presentation and for bringing this content to the SANS community. To our audience, we greatly appreciate you listening in. For a schedule of all upcoming and archived SANS webcasts, including this one, you can visit sans.org/webcast. Until next time, take care, and we hope to have you back again for the next SANS webcast.
Thank you, everyone.